NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations using the definition. We will follow a precise 3-step algorithm and apply it to an example. We will now walk through a complete example, step by step. Solve the equation, floor of 2x minus 1 equals 4. We begin with the definition. If the floor of f of x equals n, then n is less than or equal to f of x, and f of x is less than n plus 1. Step 1. Identify the integer n. Here, the right side is 4, which is an integer, so n equals 4. Step 2. Apply the definition. Replace the floor with a double inequality using n equals 4. That gives 4 less than or equal to 2x minus 1, and 2x minus 1 is less than 5. Step 3. Solve the double inequality for x. First, add 1 to all 3 parts. Then, divide everything by 2 to isolate x. Let us visualize the solution on a number line. A closed point at 2.5 and an open point at 3, with the interval shaded in between. Therefore, the solution set is all x in the interval from 2.5, inclusive, up to 3, exclusive. Summary. 1. Use the definition of the floor function to remove brackets. 2. Convert to a double inequality with n less than or equal to f of x, and f of x less than n plus 1. 3. Solve the double inequality carefully, respecting inclusions and exclusions. For practice, try solving floor of 3x plus 2 equals negative 2. Up next, explore the fractional part function and its properties. Great work following the algorithm precisely. Keep practicing to build fluency. Example. The equation is floor of x plus 1 plus floor of negative x plus 4 equals floor of x plus 2. Step 1. Use the integer shift property of the floor function. If n is an integer, then floor of x plus n equals floor of x plus n. Now, we apply that to each bracket. Step 1. Extract integers from brackets. We rewrite the equation as parenthesis floor of x plus 1 close parenthesis plus parenthesis floor of negative x plus 4 close parenthesis equals floor of x plus 2. Quick challenge. Can you simplify by canceling the common floor of x on both sides? Step 2. We simplify by subtracting floor of x from both sides and combining constants. This uses a simple algebra fact. A plus b equals a plus c implies b equals c. Step 2. Isolate the floor of negative x. We get floor of negative x equals negative 3. We'll highlight the negative 3. Tip. 1 plus 4 equals 5, and 2 minus 5 equals negative 3. Step 3. Apply the definition of the floor function. Floor of y equals k if, and only if k is less than or equal to y, and y is less than k plus 1. Step 3. Apply the definition of floor. With y equal to negative x and k equal to negative 3, we have negative 3 less than or equal to negative x and negative x less than negative 2. We will highlight the bounds minus 3 and minus 2. Step 4. Multiply the inequality by negative 1, which reverses the inequality signs. If it is less than or equal to b, then negative a is greater than or equal to negative b. Step 4. Solve for x. The solution becomes 2 less than x and x less than or equal to 3. We will display it as 2 is less than x and x is less than or equal to 3. Therefore, the solution set is x in the open interval 2 to 3, with 3 included. We will solve a floor function inequality step by step, exactly following the shown algorithm. First, we display the example and the problem statement. Now step 1. We use the definition of the floor function. Floor of u equals n if and only if n is less than or equal to u and u is less than n plus 1. We apply this to the expression inside the brackets. Step 2. We use the subtraction property to isolate the term with x. Subtract 1/5 from all parts of the inequality. Step 3. We simplify the fractions. 1 minus 1/5 is 4/5, and 2 minus 1/5 is 9/5. Step 4. We apply the division property to solve for x. Divide the entire inequality by 2. Then, we will visualize the solution on a number line. We will follow the structured algorithm precisely. First, display the label example. Then show the problem in bold orange math notation. Now, apply the integer property of the floor function. Show the rule in a glowing blue tip box. Then title the step. Finally, transform the equation by moving the integers outside the brackets and highlight the changed integers in orange. Next, combine like terms to isolate floor expressions. Show the rule box. Add the step title. Then isolate and simplify to get 0 on the right side, highlighting the 0 in orange. Consider case 1. Display the reflective property for integers. Add the step title. Then deduce that x equals 0 in this case. Now, consider non-integer x. Show the corresponding property. Add the step title. Then conclude the interval for x. Finally, state the solution set. Show the union rule. Add the step title. Then present the solution set and celebrate with a green confetti-styled answer text. To keep our visuals engaging, here is a brief we will follow a clear 5-step algorithm to solve the equation with a floor function. Here is the problem. We solve the equation x squared minus 4 floor of x plus 4 equals 0. Step 1. Let n be the floor of x. Then we rewrite the equation in terms of n. From x squared minus 4 floor of x plus 4 equals 0, we get x squared plus 4 equals 4 floor of x, which becomes x squared plus 4 equals 4n. Step 2. Use the definition n less than or equal to x less than n plus 1. Square the inequality, add 4 to match x squared plus 4, and substitute 4n for x squared plus 4. This yields n squared plus 4 is less than or equal to 4n, which is less than n plus 1 squared plus 4. Step 3. Solve the left-hand inequality n squared plus 4 less than or equal to 4n. That simplifies to n squared minus 4n plus 4 less than or equal to 0, which is the square of n minus 2 less than or equal to 0. A square cannot be negative, so it must be 0. Therefore, n equals 2. Step 4. Check the right-hand inequality, for n is less than n plus 1 squared plus 4. Rearranging gives n squared minus 2n plus 5 is strictly greater than 0. Its discriminant is negative 16, so the quadratic is always positive and imposes no restriction on n. Step 5. Intersect the results. Real numbers intersected with the set 2 gives 2. Substitute n equals 2 back into x squared plus 4 equals 4, n to get x squared equals 4. So x equals plus or minus 2. Checking the floor condition shows only x equals 2 works because floor of negative 2 is negative 2, not 2. Therefore, the solution is x equals 2. Final answer x equals 2. The problem is x cubed minus floor of x equals 3. Rule, floor function definition. We let floor of x equal n, where n is any integer. Step 1. Assume the floor of x is an integer, n. Then substitute into the equation. Rule, algebraic isolation. Move n to the right and take cube roots. Step 2. Solve for x in terms of n. Rule, substitution. Replace x in the floor expression with the derived form. Step 3. Substitute x back into the floor expression, still remembering that floor of x equals n. Rule, floor inequality. If the floor of y equals n, then n is less than or equal to y, and y is strictly less than n plus 1. Step 4. Turn the floor into an inequality, and then remove the cube root by cubing all parts. Step 5. Test integer values for n in the inequality n cubed less than or equal to n plus 3, less than or equal to n plus 3, less than n plus 1 cubed. We check 0, 1, and 2 to find which one works. Rule, solution finalization. Use n equals 1 to solve for x. Step 6. Substitute n equals 1 and compute x. Then present the solution set. Quick summary. We define the floor as an integer n, isolated x, use the floor inequality. We show the example label. Next, here is the problem statement in bold orange. The floor of 3x minus 5.2 equals 2 and 3/7. Step 1. Analyze the left side. Rule box, floor function range. The floor of any real number is always an integer. Here, the left side is the floor of 3x minus 5.2, so it must be an integer. Step 2. Analyze the right side. Rule box, constant type. 2 and 3/7 is not an integer. Therefore, the right side is a non-integer number. Step 3. Compare both sides. Rule box, definition of equality. An integer cannot equal a non-integer. Therefore, this equation has no solution. Let's begin with the problem statement. Step 1. Apply the integer out-of-floor rule. Because 3 times the floor of x is always an integer, we can move it outside the floor. Now, let's show the simplified equation. Quick challenge. Can you explain why that move is valid? Because integers pass through floors unchanged. Step 2. Combine like terms and distribute. We'll use the distributive property on the right. Then we simplify to an equality with like terms on both sides. Step 3. Isolate the floor term. We subtract 2 times the floor of x from both sides. This gathers all floor terms on the left. Step 4. Divide to solve for the floor of x. We divide both sides by 2. This gives the value of the floor of x. Step 5. Convert the floor equality into an inequality range. The definition of the floor function translates a single value of the floor into a half-open interval for x. Let's write that interval inequality. Step 6. Express the solution set in interval notation. We now state D equals the half-open interval from -4 including to -3 excluding. Summary. We will solve the equation. Now, we'll apply a key identity for the floor function. Then we'll rewrite the left side and simplify it. Before moving on, a quick challenge to predict the next step. Next, substitute that simplification into the original equation. Now, we use the definition of the floor function to turn our equation into an inequality. Let's convert it to an inequality and then isolate x. Finally, we will write the solution set and celebrate with confetti. Example. We will solve bracket x equals 5/6x, following the algorithm step by step. First, display the problem in bold orange. Step 1. Substitute the floor function definition. We write x as bracket x plus p, where p is the fractional part with 0 less than or equal to p strictly less than 1. Substitute this into the equation to get bracket x equals 5/6 times left bracket x plus p right. Quick challenge. Why must p be less than 1? Step 2. Distribute the fraction. Use the distributive property. Bracket x equals 5/6 bracket x plus 5/6p. Step 3. Group terms with bracket x. Use subtraction to isolate like terms. 5/6 p equals bracket x minus 5/6 bracket x. Step 4. Simplify the expression. Combine like terms. 5/6 p equals bracket x over 6. Step 5. Solve for the fractional part p. Multiply both sides appropriately. We get p equals bracket x over 5. And remember, 0 less than or equal to p less than 1. Step 6. Determine the range of bracket x. Substitute into the inequality for p. 0 less than or equal to bracket x less than 5. Step 7. List possible integer values. Since bracket x is an integer, it can be 0, 1, 2, 3, or 4. Quick challenge. Why is 5 excluded? Step 8. Calculate the final solutions for x. From bracket x equals 5/6x, we get x equals 6/5 times bracket x. Now compute each case. Step 9. Final solution set. Collect all values in green. Summary. We used x equals bracket x plus p, with 0 less than or equal to p less than 1, isolated p bounded bracket x, and computed x for each integer value. Next topic suggestion. Equations with fractional parts, such as brace x brace. P bounded bracket x, and computed x for each integer value. Next topic suggestion. Equations with fractional parts, such as brace x brace. Example. Our problem is to solve the equation, floor of 10 to the x equals 3. Step 1. Apply the definition of the floor function. The rule says, floor of u equals n if and only if n is less than or equal to u and u is strictly less than n plus 1. So with n equal 3 and u equal 10 to the x, we get 3 less than or equal to 10 to the x is less than 4. Step 2. Solve the inequalities using logarithms. The logarithm rule says b to the y equals x if and only if y equals log base b of x. Apply base 10 log to 3 less than or equal to 10 to the x to get log 10 of 3 less than or equal to x. Apply base 10 log to 4 greater than 10 to the x to get log 10 of 4 greater than x. Step 3. Determine the solution interval. Intersect x greater than or equal to log 10 3 with x less than log 10 4. The result is the half-closed interval from log 10 3 inclusive to log 10 4 exclusive. Final answer x lies in the interval from log 10 3 inclusive to log 10 4 exclusive. Log of open bracket x close bracket equals 1. We will solve it fully and precisely. Step 1. Convert to exponential form using the definition of the logarithm. The rule states log base a of n equals x if and only if n equals a to the x. Since no base is written, the base is 10. Let's write the step title and apply the rule. We will rewrite the equation accordingly and highlight what changes. Quick challenge. What is the base of the natural logarithm? The answer is e, the Euler's number. Step 2. Use the property of the greatest integer or floor function. The rule says, if the floor of x equals n, then n is less than or equal to x, and strictly less than n plus 1. Let's title the step and apply this to the equation. X equals 10. We'll write the inequality for x. Step 3. State the solution set in interval notation. We'll write the final answer clearly. Then we will celebrate the result briefly. We will solve an exponential equation that involves the floor function. First, here is the example we will work through. Step 1. We rewrite the equation using base 2. 4 to the floor of x equals 2 to the power 2 times the floor of x. Step 2. We substitute y equals 2 to the floor of x. Because the floor of x is an integer, y is a positive power of 2, so y is positive. Then the equation becomes y squared minus 6, y plus 8 equals 0. Step 3. We factor the quadratic. Y squared minus 6, y plus 8 equals quantity, y minus 2 times quantity, y minus 4 equals 0. So y equals 2 or y equals 4. Step 4. First case, y equals 2. Then 2 to the floor of x equals 2 to the first power. So the floor of x equals 1. By the definition of the floor function, 1 is less than or equal to x, and x is less than 2. So x is in the interval from 1 to 2, including 1 but not including 2. Step 5. Second case, y equals 4. Then 2 to the floor of x equals 2 squared. So the floor of x equals 2. By the floor definition, 2 is less than or equal to x, and x is less than 3. So x is in the interval from 2 to 3, including 2 but not including 3. Step 6. Combine the two intervals. The union of the interval from 1 to 2 and the interval from 2 to 3 is the interval from 1 to 3. So the full solution set is x is in the interval from 1 to 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.